go. So let us continue chapter 11. We're going to talk about power series. The definition of power series and the condition when power series are convergent. Let us officially write down definition of power series. A power series is defined this way. So first of all, it's a series. So we're going to use the summation notation. Then it has some coefficients denoted by C sub n. So C sub n's, these are coefficients depending on n. Coefficients. And then you have a term involving x. You have parentheses x minus a number, which is our center, x raised to power n. So a is also a number. And this series n starts from 0, goes to infinity. Goes to infinity. We have a theorem. Our goal is to connect functions with power series. If f has a power series, representation then f as a function can be written as the sum c sub n x minus a to power n, and start from 0, goes to infinity, and you have this condition. The absolute value of x minus a, the distance between x and a, is less than r. So the distance between points and a, the center, is less than the radius. This is the radius of your power series. Do we have a formula to connect Cn, C sub n to f? We have formulas. C sub n can be defined as the nth derivative of f evaluated at a divided by n factorial. So if you have a function and that function has power series representation, that power series representation can be written this way: the sum c sub n x minus a to power n, while n ranges from 0, goes to infinity. When you're dealing with functions like f of x, remember that when you have a series and the series is convergent to that value, in this case you have a function, they have the distance between x, those x values. The distance between x and the center must be less than a radius. Later on, we're going to learn how to calculate this radius. And these coefficients, they are all related to the derivatives of function f. So this power series representation is called Taylor series for function f. If the center is at the origin at 0, we call it Maclaurin series. So let's write these down, then go over a couple of examples. So Taylor series. Of function f at a, f of x is equal to the sum c sub n x minus a to power n, and starts from 0, goes to infinity. C sub n is calculated as the nth derivative of f at a divided by n factorial, and the distance between x to a is less than r. When it comes to Maclaurin series, Maclaurin series is actually Taylor series of function f at a equal to 0. So we represent it this way. We say that, hey, f of x is equal to the sum c sub n. Now you only have x minus 0 to power n, and starts from 0, goes to infinity, or in simplified form, it is equal to the sum cn x to the n, and starts from 0, goes to infinity. With the same conditions, in this case, x minus 0, absolute value is less than r, and c sub n is equal to nth derivative of f at 0 divided by n factorial. So in general, you have Taylor series. A can be any number. In special case, when a is 0, we call Taylor series a Maclaurin series. So let us write down these two on the right-hand side of the board. Then we're going to go over some examples, writing down the Maclaurin series for known functions. So Taylor series of function f at a is f of x equals to the sum c sub n x minus a to power n, and start from 0, goes to infinity. C sub n is the nth derivative of, this is the nth derivative of f evaluated at a over n factorial, and the distance between x to a is less than r. And we just learned that Maclaurin series is nothing but Taylor series, but the center is at 0. Is Taylor series when a is equal to 0. Example. This example says, well, find the Maclaurin series of function f of x e to the x, or find the Maclaurin expansion of function f of x equals to e to the x. Okay. We know Maclaurin series is nothing but Taylor series when a is equal to 0. So what do we have? We have f of x equals to the sum c sub n x minus a to power n. Since it's Maclaurin series, a is equal to 0. So you have just x to the n. N starts from 0, goes to infinity, and we know that c sub n is the nth derivative of n. A is equal to 0, so here we plug in 0 divided by n factorial. Okay, this is equal to c sub 0 x to 0 plus c sub 1 x to the first plus c sub 2 x squared plus c sub 3 x cubed plus the rest of the terms. Okay, what is c sub 0? 0. What is c sub 1? What is c sub 2? These are all numbers, remember that. So c sub 0 is equal to the zeroth derivative of function at 0 divided by 0 factor. Note that the zeroth derivative of any function is equal to that function. So when we have function e to the x and we take the zeroth derivative, when we put it in parentheses, it means that we're dealing with the derivative. We're not raising it to an exponent. When you use parentheses, it means that you are dealing with derivatives. The zeroth derivative of e to the x is equal to e to the x. Okay. So the zeroth derivative of f is e to the x, but we evaluate that at 0. X is equal to 0. So e to 0, 0 factorial is 1. So you have 1 over 1 or 1. We found c sub 0, which is just 1. 1 times e to x to 0. X to 0 is also 1. So you get 1 times 1 plus. Now let us calculate c sub 1. C sub 1 is the first derivative of f evaluated at 0 divided by 1 factorial. Okay, the first derivative of e to the x, the first derivative of e to the x is e to the x. So we have e to the x, but what is x? X is still 0. Divided by 1 factorial. We get 1 over 1, which is 1. So c sub 1 is also 1. 1 times x plus. Let us calculate c sub 2. C sub 2 is the second derivative of f. Second derivative of f evaluated at 0 divided by 2 factorial. The second derivative of e to the x is also e to the x, but what is x? X is 0. Divided by 2 factorial e to power 0, which is 1 over 2 factorial, or just 2. So this is our c sub 2. C sub 2 is 1 over 2 factorial x squared plus c sub 3. We continue this process. C sub 3 is equal to the third derivative of f at 0 divided by 3 factorial. Again, the derivative of e to the x, they are all equal to e to the x. So we get e raised to 0 divided by 3 factorial, which is 1 over 3 factorial, or 1 over 6. So c sub 3 is 1 over 3 factorial x cubed plus the rest of the terms. This is expanded form. This is expanded form. Which can be written in compact form as, well, okay, this guy is equal to the sum. Here we have the powers of x to the n, divided by n factorial, while n starts from 0, goes to infinity. And this is your compacted form. So e to the x, the function e to the x has power series representation, which is x to the n divided by n factorial, while n starts from 0, goes to infinity. So this is compact form. Very well. So I expect you to ask, what is the radius of convergence? Well, to find the radius of convergence, you're going to get back to the tests that we learned before. Remember that we learned that, for example, for series, the sum a sub n, and start from 0 to infinity, the limit of an plus 1 divided by an while n approaches infinity was equal to L, and L needs to be less than 1. In that case, we say that the series is a convergent series. It was our ratio test. Ratio test for a series to be convergent. We're going to do the exact same thing for our power series. So here we need to form the limit of absolute value of an plus 1. X to the n divided by n factorial is actually our an. So it's going to be x raised to n plus 1 divided by n plus 1 factorial over a sub n, which is x to the n over n factorial. We're going to take the limit, and this limit as n approaches infinity must be less than 1. Okay, let's start simplifying this fraction. So we need to multiply these two, and then we need to multiply these two and simplify our fraction here. So we get the limit of n factorial times x to n times x divided by n plus 1 factorial, n plus 1 factorial times x to the n, and this guy must be less than 1. So let me erase this part. I need a little bit of more space. Okay. So we know that this guy is equal to the sum x to the n over n factorial, and starts from 0, goes to infinity. Very well, you can cancel out x to the n and x to the n, and here you have n factorial divided by n plus 1 factorial. N plus 1 factorial can be written as n plus 1 times n factorial, another property of n factorial. So this limit becomes the limit of absolute value of n factorial times x divided by n plus 1 times n factorial as n approaches infinity. We can cancel out n factorial and n factorial. what's left? You have, and this guy must be less than 1. You have the limit of x divided by n plus 1. As n approaches infinity, you have x over infinity, which is 0. This limit for any value of x is always 0. So this limit for any value of x is 0. So what's the meaning of that? It means that we have a 0 less than 1. So in this case, since this is a true statement, it means that this series is convergent over real line, negative infinity to positive infinity. It means that our series is convergent over negative infinity to positive infinity. That's the meaning of that. So let us write down the summary, how to find the radius of convergence here. Radius of convergence for series sum an and starts from 0 to infinity. The radius of convergence is r, which is equal to 1 over the limit of absolute value of an plus 1 over an while n approaches infinity, or this limit is equal to 1 divided by r. So as you can see, this limit is equal to 0. 1 over 0 is infinity, so that's why we say that this series is convergent over negative infinity to positive infinity. In this case, you get your x bounded between negative r to r. Since our r is infinity, x is bounded between negative infinity to positive infinity. Okay, so let's suppose we have this example. The example says, find the Taylor series find the Taylor series of function f of x equals to e to the x. Since we are dealing with Taylor series, we need to have a. The center, suppose your center is equal to 1. Okay, very well. Remember that the Taylor series is f of x equal to the sum Cn x minus a to power n, and start from 0, goes to infinity, and Cn is nothing but the nth derivative of the function evaluated at a over n factorial. Very well. So our a is equal to 1. It means that wherever we see a, we're going to substitute that for with 1. So here we have c sub 0 x minus 1 to power 0. C sub 1, x minus 1 to the power 1. C sub 2, x minus 1 to the power 2, and so on. We'll continue this process. So our job is to find C sub 0, C sub 1, C sub 2. Where did we expand that for? C sub 0 is the zeroth derivative of this function evaluated at 1 over 0 factorial. We all know the derivative of e to the x, zeroth derivative, is equal to the function itself. So it's going to be e to the x, but what is x? X is 1. X is 1. Divided by 0 factorial, by convention, is just 1. So you have e over 1. C sub 1 is equal to the first derivative of f evaluated at a. It happens a is also 1 divided by 1 factorial. The first derivative of the function is just e to the x. X is also 1, so e to the first over 1 factorial, or e over 1 factorial. C sub 2 is equal to the second derivative of f evaluated at 1 over 2 factorial. The second derivative of e to the x is also e to the x, so you get e to the first divided by 2 factorial, which is equal to e over 2 factorial. We can continue this process. So e to the x, the Taylor series at a equals to 1 is equal to c sub 0 is e. E times 1 is expression raised to 0 is 1 plus c sub 1, which is e over 1 factorial times x minus 1 plus c sub 2, which is e over 2 factorial x minus 1 to the second power, dot, dot, dot. So this is your expanded form. You can write this in compact form, e to the n, e times x minus 1 to power n divided by n factorial, n starts from 0 goes to infinity. Okay, now I expect you to ask, what is the radius of convergence? Now let us find the radius of convergence. To find the radius of convergence, you need to find the limit of absolute value of an plus 1 over an while n approaches infinity. And this, whatever it is, it must be less than 1. Otherwise, we don't have convergence. So step by step, we're going to calculate this limit. So this limit is equal to the limit of absolute value, an plus 1. So you have e times x minus 1 to n plus 1 divided by n plus 1 factorial. This is an plus 1 divided by a sub n, which is e x minus 1 to power n divided by n factorial, n goes to infinity. We can quickly just cancel out e and e. What's left? You're left with the limit of absolute value of x minus 1 to power n times x minus 1 times n factorial divided by x minus 1 to power n times n plus 1 factorial, which is n plus 1 times n factorial, and n goes to infinity. Well, we can cancel out more things. n factorial, n factorial, x minus 1 to power n, x minus 1 to power n. What is left? You have the limit of absolute value of x minus 1 divided by n plus 1 as n goes to infinity. The only problem is x. So you're going to just take this absolute value and put x minus 1 inside absolute value. So what do we have? We have the limit of some values over n plus 1 as n goes to infinity. This is equal to 1 over n plus 1 as n goes to infinity is 0. So this guy is 0 times absolute value of x minus 1, which is always 0. Okay, what's the meaning of that? It means that r, which is 1 over divided by this number that we found as 0 is going to be infinity. So r is going to be infinity. So it means that your x minus a is between negative infinity to positive infinity, or x is again is between negative infinity to positive infinity. All of these x values are all accepted. We can represent this as negative interval of convergence as negative infinity to positive infinity as interval of convergence. So the interval of convergence is negative infinity to positive infinity. So when we write the absolute value of x minus a less than r, it means that x minus a is less than r, larger than negative r. In this case, we found r to be infinity, so x minus a, which is x minus 1, is between negative infinity to positive infinity, but adding 1 to all sides, it doesn't change the infinity. You get x between negative infinity to positive infinity. The radius of convergence is infinity, and the interval of convergence is between negative infinity to positive infinity, or the whole horizontal line. Very well. So when we use Taylor series or Maclaurin series, you're actually having some approximation for functions. It's not the exact value. You need to have some conditions to met. Then we say that, hey, this function is actually equal to its Taylor's expansion. We have a theorem here. So let us write down the theorem, the detail of that theorem. Remember that when you're using Taylor series, Maclaurin series, you're trying to approximate the function using some power terms. X to the n or x minus a to the power n helps us to use some terms, linear terms, quadratic terms, cubic terms, and the rest of the polynomial forms to approximate a function. Here we have a theorem. This theorem says, let f of x be equal to Tn of x plus Rn of x. Tn of x is the nth Taylor polynomial for the function where T sub n of x is the nth degree Taylor's polynomial. And R sub n is going to be the error. R sub n of x is the error. So if you have this function, f of x equals to t sub n plus r sub n, and the condition is the limit of the error, Rn of x, as n approaches infinity, is equal to 0. Note that we are working with the radius of convergence R and the center A. So if you have a function written as the Taylor expansion plus the error, because there is a difference between this actual value and the Taylor polynomial. And note that you have this condition as well, the limit of the error as n approaches infinity is equal to 0. Then for sure you can say that, f of x is equal to its Taylor's polynomial over x minus a less than r. So this theorem says if you can investigate that the limit of this error is equal to 0, for sure your function is equal to its Taylor's expansion. There is no worry about some other terms that make a huge difference between your function and its Taylor's expansion. So now I expect you to ask, do we have something that we can calculate the error? We have Taylor's inequality that help us to find some boundaries for the error. Taylor's inequality. This is important, guys. So if the higher derivatives of the function, if the n plus 1 derivative of the function is bounded, let's just use for any x, is bounded less than equals to m. M is just a constant. Over absolute value of x minus a less than r, when the distance between x and a is less than r, then let's just write d instead of r to avoid the confusion between d and r. So if the higher derivative of your function is less than equals to m over the distance between x and a is less than d, d is just another number. Let's just distinguish these two between r and d. Then we have the following condition. Then for sure you can say that absolute value of the error is less than or equal to m over n plus 1 factorial n plus 1 factorial times x minus a to power n plus 1 over x minus a less than equals to d. When you have this, you can take the limit of both hand sides and show that the limit is equal to 0, then you have this conclusion. Note, you use this inequality to show that the limit of Rn as n approaches infinity is equal to 0. That's the use of this inequality. So the theorem says if f of n is Tn plus Rn, we have a Taylor's expansion and a term that's related to error. If you can show that the limit of Rn, the limit of the error is equal to 0, then for sure this theorem assures you, guarantee you that f of x is equal to its Taylor's polynomial. But to find the limit, to show that the limit is equal to 0, we have to use Taylor's inequality, which says if you have this condition that the absolute value of the higher derivative of the function is less than equals to m, it's bounded by an upper bound by a function, a constant function, then the absolute value of Rn, the absolute value of error, is less than equals to m, which is a constant, that constant function, over n plus 1 factorial times the absolute value x minus a to power n plus 1. Then we can quickly use this and find the limit of Rn. Very well. So example, how do we use this theorem? How do we use Taylor's inequality? Give us an example. Well, okay. Example. This guy says, prove that function f of x e to the x is equal to its Maclaurin series. Very well. So remember the theorem. Let me write them down here. The theorem says if f of x is equal to Tn of x plus Rn of x, and if the limit of Rn of x, the error, as x approaches infinity is equal to 0, then f of x is equal to its Taylor series over x minus a less than r. And Taylor inequality says if the nth derivative of n plus 1 derivative of f is bounded by a constant function like m, then Rn of x is less than or equal to m divided by n plus 1 factorial times absolute value of x minus a raised to d, and here you have x minus 8 here to n plus 1 and this guy is less than D. Okay, perfect. So, you know these two. Let us check our function f of x. The function f of x is e to x. This is x minus a. Our goal is to apply this theorem. To apply the theorem. But to apply the theorem, we need to show that the limit of Rn is equal to 0. So we need to show that the limit of Rn of x, the error as n approaches infinity, is equal to 0. So let us see if we can apply Taylor's inequality. Let us check the Taylor's inequality. Taylor's inequality says if the n plus 1 derivative of the function is bounded above by a constant function over this interval, x minus a is less than d, then the error function is less than or equals to that quantity. Then we can apply the limit. We know that. The zeroth derivative of e to the x is equal to the first derivative of e to the x, is equal to the second derivative of e to the x. They are all equal to e to the x. For exponential function, e to the x. Remember e to the x. The function behaves like this. This is your function, e to the x. But note that we have boundaries for our x. Okay. X, absolute value of x, is less than d. Remember that a for Maclaurin series is equal to 0. So it says that my x is bounded between negative d and d. My x on the horizontal axis is bounded between negative d and d. So suppose this is negative d and this is your d. So on x-axis, your x is bounded between two numbers, negative d and d. And here, when you look at your function e to the x, your y values take on the maximum value of e to the d. E is a number, d is a number, so this is a number. So what's the meaning of that? It means that the nth derivative of the function, which is equal to e to the x, they can be bounded by the maximum value e to the d. So the absolute value of e to the x is less than e to the d. This is your m. Do we have m? Yes, we just found it by analyzing e to the x. We found m. So this constant function is e to the d. Very well. So Taylor's inequality says, so Rn of x, the absolute value of Rn of x, is less than or equals to m, which is e to d, times absolute value of x to n plus 1 divided by n plus 1 factorial. Well, now you can easily take the limit. Let's take the limit. So here you have the limit of absolute value of Rn of x while n approaches infinity less than equals to the limit of e to power d, which is a number, divided by n plus 1 factorial times x raised to n plus 1. So you have a number divided by infinity, which is 0. 0 times absolute value of x, the whole thing is equal to 0. So the limit of Rn is equal to 0, and the theorem is satisfied. Very well, give us another example. So let's work with sine function. Scientific functions. Prove that f of x equal to sine of x is equal to its Maclaurin series. Okay. What are we interested in is applying the theorem that we have. We want to apply our theorem. To apply the theorem, we need to show that. So we need to show that the limit of Rn as n approaches infinity is equal to 0 for sine function. So we need Taylor's inequality. Taylor's inequality says if the higher derivatives of the function sine x is less than equals to a constant function. It's so obvious. We already know the behavior of sine function. F of x is equal to sine x. We know that the first derivative of this function is cosine. The second derivative of this function is negative sine. The third derivative of this function, negative cosine, and so on. So it oscillates between sine and cosine. And we already know that both sine x and cosine x, both of these two functions are bounded between -1 and 1. It means that the maximum value they take is 1. So obviously, m is 1. So the n plus 1 derivative of function is less than equals to m, which is 1. Well, okay. So since the condition is met, it means that the error function for sine is less than equals to 1 divided by n plus 1 factorial x to power n plus 1. And now here you have the limit of left, which is less than equals to the limit of right, limit of absolute value of Rn of x, the error function as n approaches infinity, is less than equals to the limit of 1 over n plus 1 factorial absolute value of x raised to n plus 1 as n approaches infinity. This guy is 0. 0 times absolute value of x is equal to 0. So the limit of Rn of x as n approaches infinity is 0. It means that the limit of Rn is 0. So we can apply our theorem.